peur.
Mais si c'est là.
Hello, Anna. Do you hear us?
Yes, I do. Good morning.
Perfect.
Good afternoon.
So we can start the defense. I will start by presenting the jury member, and then I will let Lee present his PhD. So the jury is composed of two reviewers, Xavier Hinaut from Centre de Recherche INRIA in Bordeaux, Anna Huang, who is assistant professor in MIT, Emmanouil Benetos, Director of Research and Reader at Queen Mary University of London, Chloé, Braud, who is Chargé de Recherche, CNRS in Toulouse, myself, so I'm Directeur de Recherche, CNRS here. Bigo is Professor and works in Bordeaux as well. Marc-Masi is a professor working in CRIStAL, and Michaela Keller, who is at the conference Université of Lille. Lee, you have 45 minutes to present your work, and then there will be a question. The floor is yours.
So welcome to my PhD defense. So I'm Dinh-Viet-Toan, and I will present the work I've done during these last 3 years under the supervision of Marc-Masi, Bigo, and Michaela Keller. So my thesis is entitled Modeling Symbolic Music with Natural Language Processing Approaches. So in other words, we want to study to what extent natural language processing tools, that is to say, for example, artificial intelligence tools for text processing, can be used to represent or to process symbolic music. So first of all, let's start with some music. So we'll play here an extract from Symphony No. 5 from Beethoven. And so while you're listening to this extract, please try to think about how you would describe what you hear. So to describe this extract, I could say something like there is a musical phrase which is passed through the violins to the woodwinds as a kind of dialogue between them. So what is interesting in what I've just said is that the terms I've used are borrowed from a lexical field which is usually used to describe the elements related to natural language more than music, like for example, a phrase or a dialogue. Sometimes we often use other terms, like for example, the vocabulary, to say that, for example, Beethoven's musical vocabulary is not the same as Shostakovich's vocabulary, for example. And we often go as far as talking about musical language. So this question of is music a language has been studied, but is also very debated. So we can wonder to what extent music and language are really similar or not. So first of all, they do share some fundamental similarities. Like in terms of modalities, most language and music do have an auditory form and a written form. Then in terms of representation also, there can be some similarities in terms of segmentation, but also when seen as sequential data. Like for example, text can be seen as a sequence of words in the same way as music can be seen as a sequence of notes. And finally, at a higher level, there can be some grammatical rules that can lead to some expectancy phenomena. For example, in language, if I say the sentence, the cat is eating the, you are expecting a word like mouse at the end. In the same way, in music, you can have this kind of expectancy phenomenon. For example, if I play this extract, there is something missing, something like that, which concludes well the musical phrase. So we have these similarities between music and language, but also major differences, like the temporal dimension, which does not play the same role in language and music, the notion of polyphony in music, that say multiple notes playing at the same time, and also a kind of polymorphism of musical symbols, that say that a single note can carry multiple characteristics on its own. So throughout this thesis, we wanted to study to what extent these parallels and non-parallels between language and music can be adapted or not, in the context of computer science, and in particular in the context of machine learning. So we have seen that there are two modalities for music, either audio, that say what you hear, or symbolic music. And it's not for this last one, but I will focus on this thesis, that you say music seen as sheet music, in which we'll manipulate objects such as notes and chords. So the two fields that are involved in my thesis are, on the one hand, natural language processing, which is at a crossroad between computer science and linguistics. And on the other hand, music information retrieval, which is at a crossroad between computer science and music. And so if we look at the presence of NLP in the MRI domain, we can see that the MRI domain has more and more used NLP tools in the academic works the last few years, and in particular with the breakthrough of transformers in the NLP field. So this follows that they are between text and symbolic music, and this rising use of NLP tools in the MRI domain has motivated, at the end, the thesis about modeling symbolic music with natural language processing approaches. So for that, we first propose a map of the field of NLP tools in the MRI domain following three axes: representations, models, and tasks. So this structure is at the root of one of the main contributions of this thesis, which is a survey about NLP tools for symbolic music processing that we have published. And so in this presentation, I will also follow this structure in 3 points. And for each of the 3 axes, we have also some technical contributions that I will also present. So first of all, let's start with representations, and in particular with sequential representations. So in this part, I will mainly focus on presenting a taxonomy we propose to organize a literature about musical sequential representations as part of our survey. So we'll be talking about tokenization, that is say representing a complex content, like for example text or symbolic music, into a sequence of elements for computational processing. And so for text, there can be multiple ways to represent text as sequence. Like for example, if I take this sentence, I love singing, but it is exhausting, the elements, or what are called tokens, can be of different nature. Like for example, they can be words, characters, or subwords, like for example, prefixes or suffixes. So let's also represent music as a sequence of tokens, so that we can use the same models we use in NLP to process text, like transformers. But the problem with symbolic music is that it can be much more complex, because the score contains a lot of information. Like for example, information about pitch, information about rhythm, like rest also, information about the tempo, the structure, like bars and beats within a bar, about polyphony, that say multiple instruments playing at the same time, or polyphonic instruments by themselves, like a piano, for example, articulations, and also dynamics. And so the issue now is how can we represent all this information under a unidimensional sequence of tokens? So in the literature, there have been several propositions for this issue. And so to organize all these propositions, we propose a taxonomy describing tokenization strategies for symbolic music. And so we build this taxonomy around 2 types of tokenizations, some time slice and event-based, which can then be subdivided into smaller categories that I will describe later. And so in the following slides, I will detail how we have built this taxonomy. So first of all, given that time plays an important role in music, like being at the base of rhythm, the first way to tokenize music would be to consider regular time steps as being the limits in between tokens, so that at the end, the tokens themselves would be called what we have called time slices. And so this is typically a way to consider these piano rolls, so which is a matricial representation of music, in which the x-axis is time and the y-axis is pitch. It would be a way to consider these piano rolls as a sequence of tokens, where each token would be a slice of this piano roll. So this representation can be used in several tasks or in various instrumentations, like here for drums tokenization. However, today, most of the tokenizations are based on what we have called event-based tokens. So let's say that I am a pianist and I'm asked to play that. What would I do? So first of all, I will press the C note with a certain velocity or a certain force on the key. I will wait for 400 milliseconds, which is the duration of this quarter note, and then I will release the note. I can do the same for the E note, so press, wait, and release. And again for the G. Press, wait a little bit longer because it's a half note, and then release the note. So we managed to encode this sheet music into a sequence of elements, of tokens. And so this MIDI-based tokenization is typically the token representation of the MIDI protocol, which has been developed typically for synthesizer communication. So let's go further by looking at this tokenization, because it can be improved if we see that the not ons and the not offs token are always working in pair. Like if I press something, I have to release it one day. So it can be better to merge this not on and not on token into a pitch token and encode directly the duration. And so this is another tokenization that has been proposed, which encodes the same musical content. So this tokenization can still be improved because by looking at the values of the tokens themselves, like 400 milliseconds, it is still a non-very musical relevant unit, like milliseconds, but there is a way to encode time more musically. And so this is typically what is proposed by the Remy tokenization, in which now the time is represented as bars and positions within a bar. And so the tokens are now expressed with more musical relevant units, such as here the number of 16. So what we have seen so far with the three tokenizations is that one can choose the elements to describe music. In other words, there's a choice of what we propose to call an alphabet. So let's continue to see how this tokenization has been improved in the literature. Here we see that if we look at the token by itself, let's say the duration 4, it does not mean anything if it's not associated to other tokens before. So there is also a choice of grouping strategy to group some tokens together. For example, if we choose to group the velocity and the duration tokens together, there is this kind of super token that would be more musically relevant. Like, for example, this super token would refer to a quarter note with a mezzo piano dynamic. And so in the literature, there have been several propositions for grouping strategies in MLR. So what I have seen so far is that in an event-based tokenization strategies, there is a choice of an alphabet and of a grouping strategy. Let's continue and see now more a musical problem with this tokenization. Like, what about multi-track music or polyphonic music? Here we were only with monotrack. So this issue is tackled with the Remy Plus tokenization, where now there are additional track tokens which indicate which instrument is playing which note. And so this is typically a case of enriching the Remy alphabet with its additional track tokens. And so now there is, again, another problem, but more a technical problem. Like here we need like 30 tokens also to represent only 6 notes on the sheet list. So there would be a sequence length problem at some point. And so what we have seen so far are tokenizations in which a token represents a single elementary token, a single elementary event. That's why we have called for now these tokenizations elementary tokens. But instead, there have been propositions to build composite tokens. That is, say, a token which is a note itself and which compiles multiple characteristics of a note by itself. So by doing so, the sequence length is reduced because now what is considered as a token is the combination of all these characteristics so that the model can process smaller sequences. And of course, this raises the question of how complex the model would be afterwards to process such more complex tokens. So this is that's how we have built this taxonomy we propose to describe a tokenization strategy for symbolic music, which is only a part of our more global survey on NLP tools for symbolic music processing. And so on this subject of sequential representations, we have also 2 technical contributions that I won't develop in this presentation about tokenization expressiveness. So more precisely, we have focused on how we can improve the expressiveness of event-based tokenizations by focusing on how the expressiveness of the alphabet can be improved by using, for example, intervals instead of absolute pitch, and in terms of grouping to evaluate how the bytecode encoding, seen as a grouping strategy, can behave with different levels of polyphony. So now that we know how to represent music sequentially, we can process it through models. And so here in this part, I will mainly present one of the technical contributions about model mechanistic interpretability. So first of all, to give a quick overview of NLP tools, NLP models adapted for symbolic music processing, it began first with shallow models, then followed by deep learning models, typically recurrent models. But now, most of the models are based on attention-based models, typically transformers. And so transformers are a deep learning architecture which relies on an attention mechanism, which aims at building new representations of an input token sequence by weighting the importance of each token according to its relevance to the others. So in a sense, the model would pay more or less attention to specific words depending on the context of the phrase. For example, if I take this sentence, the conductor congratulates the singer because she sang well, the she could refer to the conductor or to the singer. But for a model which has been trained on enough data, the she is more likely to refer to the singer because of the context of the sentence. The problem, however, with these attention-based models is that they have gained in complexity these last few years because they have been larger and larger, so that they are often just considered as black boxes. So there is a subfield in model developments which has emerged, which focuses on model explainability or model interpretability. So this field aims at making a model's decision process transparent, faithful, and interpretable, and in particular through human-centered explanations. And so in NRIA, these explainability results are often just seen as secondary results, but some of them have focused, for example, on attention mechanism visualization. The approach we wanted to have in our technical contribution that I will now present is not to visualize only, but to analyze the attention mechanism, and in particular in the context of functional harmonic analysis. So for that, we propose a methodology to interpret how the attention mechanism behaves with regards to some musical characteristics. And so to present this methodology, let's make an analogy with how cognitive science studies work. So in these cognitive tasks, we have first a subject, like for example, a human being. We present a stimulus to this human being, like for example, an alarm. And in the same time, you are measuring something on this human being, like for example, an EEG. And at the end, you want to compare the behavior of this physiological remeasurement in response to the stimulus. And so we want to do the same thing, but instead of a human being, we have a transformer, and in the context of a musical task. So instead of the stimulus, we'll choose a musical characteristic that will be worth studying. Instead of the physiological measurements, we'll have a neural network feature that will quantify the attention mechanism behavior. And at the end, we want to compare this feature against the musical characteristic. In other words, we want to see if there is some contrast in the neural network feature in response to the different values of our musical characteristic. And so in the following slides, I will present what we have chosen as our musical characteristic and what we have chosen as our neural network feature. So we are in the context of functional harmonic analysis. So functional harmony is a framework that assumes that chords play different functions in a piece. Like for example, at the beginning, I've played something about expectancy, and you heard that some can bring more tension and some can bring more relaxation by ending the musical phrase. So there is a syntax to annotate these chords, and I will present this now. Let's say that you are asked to annotate this chord. First of all, we can listen to what it sounds. So we want to annotate this chord, and we can focus on multiple things. First of all, we can derive what is called the local key by looking at some chords, for example, or some other patterns, like for example, a cadence. By looking at other notes, we can derive other features. Like for example, here we see that it's a G major chord, which corresponds to the 5th degree of C major. By looking at other notes, we can derive the quality of the chord. Here we see that it's a 7th chord, which gives us some options then for the inversion. And finally, by looking at the note itself, we can derive the inversion value. And so this Roman numeral aims at describing the function of this chord, and it's on this task that we'll focus on. If we look at this image, having all these arrows, these implicit arrows when we are doing functional harmonic analysis, reminds us a little bit of these attention arrows we have in text, like in the figure I've presented just before. So the similarity between these attention arrows we have in attention-based models and these implicit arrows we have when we are performing Roman numeral analysis was a motivation at the end to consider that the attention mechanism could be used as a model explainability tool in a task of automatic functional harmonic analysis. And so first of all, let's build a model for automatic functional harmonic analysis. So we propose a model based on transformer encoders of 12 layers of 12 attention heads per layer. And it takes as an input a time slice-based tokenization because of the particularities of the task. And so we can train this model as an end-to-end model, as an end-to-end model with a corpus biased towards tonal music. And so by evaluating this model, we can derive the accuracy of the model and compare this performance to some other models which have been trained on this task. So we don't have the state-of-the-art performances on this task. However, we are still comparable to the state-of-the-art models. And what we really wanted to focus on is more on the explainability side of the model, more than the performances of the model itself. So I have presented a little bit what is functional harmonic analysis, and it particularly involves the local key. And it will be on this feature of the local key that we want to focus on. So to give an intuitive and more musical idea of what is a local key, we can listen to this extract, in which we switch from one key in yellow to another key in green. So this process of changing key is called a modulation, and when we'll listen to this extract, please try to think of to focus on the changing point, like there is something which shifts, something which can sound brighter. So for us human, we could hear that something shifts here. So it's the local key. But what about a model? In particular, if you want to focus on the attention heads, do the attention head relevant for the annotation of the local key remain the same before the modulation and after the modulation? And so that will be our underlining question for this part. So if we go back to our methodology, we have now chosen our musical characteristic. That would be the local key. And so now we want to choose a neural network feature that will describe this attention head relevance. And so for that, we have chosen layer relevance propagation, which is a technique designed to evaluate how relevant each neuron in a trained neural network is for its prediction. And so in practice, it works like that. You first consider a trained model on a classification task, and you perform a classic forward pass by keeping track of the logics at the output of each neuron. In particular, you keep track of the last logit, and you perform from there an LRP backward pass. That's to say that you want to see what was the relevance of this neuron for the output, what was the relevance of this neuron for the output, etc., etc. And so for a more visual example, we can see how it works on text data. Like, for example, if you consider a Llama 3 model, so in text, which has been trained for next word prediction, we can pass the same text as the input of the model, but we only change the prompt at the end. So, for example, what is the purpose of Artemis 2 versus what is the purpose of Artemis 3? And what we see is that the relevant token for the next word prediction is not the same, depending on the prompt, like orbit versus length. And so here we managed to have the relevance of each token. But what we want to have is the relevance of the attention heads, which are in between, inside the model. And so for that, we propose an object that we have called an LRP map, which describes the contribution of each attention head to a prediction. So if we take again our analogy with cognitive science, this LRP map would be similar to a mapping of our brain into like different zones, like a cerebral cortex, a noctural cortex, etc. And so we want to use this LRP map as our neural network feature that we'll use to quantify the attention head relevance. And so at the end, the last step is to compare this feature against the musical characteristic. And so let's see where we are going. So at the beginning, we have some music. We can tokenize it, and there are some local key labels which are associated to each token. We can derive an LRP map from each pair token label. And then if we compute some distances between the LRP maps, some LRP maps can be very similar, while some pairs of LRP maps can be very different. So we can also group all these values together. Like, for example, this value will fall at the intersection of these two chunks, and this other value will fall somewhere here. And so if we compute all the pairwise distances between the LRP maps, we derive a distance matrix between the LRP maps. So again, we can read this matrix as such, like this red zones would mean that similar attention heads were used to label these two tokens, while blue zones would mean that different attention heads were used to label these two tokens. And so we have these distances between LRP maps, and we can relate it with the actual local key labels. So here we have a modulation, for example, from G major to G major. And so if we look at one pair of tokens, it can be labeled the same. Like, for example, they are both in G major. And then if we compute the distances between the LRP maps for which the tokens were labeled the same, we can derive a distribution of such distances. And we can do the same for pairs of label which have been labeled differently, and we can derive another distribution. So the initial question of are the relevant heads for the annotation of the local key remain the same before the modulation and after the modulation can be now summarized as just comparing two distributions. So we can do that. So by comparing these two distributions, we see that the two distributions are distinct. That is to say that the relevant attention heads are different when we are changing. And in particular, the average value of the average distance is lower when we have the same level compared to when we have different labels. This means that the attention heads which are relevant for the annotation of the same local key are more similar than when we are annotating different local keys. So this is an expected result since our model has been trained on local key labeling. But this first indicates that our chosen neural network feature, so our NLP maps, captures well the attention head relevance. However, beyond that, we have also two additional results that I'll present. The first result is, does the model learn more than just local key labeling? In particular, what if we consider other labels as our stimulus instead of just local key? For example, degree of the chord, the quality of the chord, inversion, or even non-harmonic feature, like for example, rhythmic intensity. So what we see is that there are other harmonic features that are also present in the model, like the degree and the quality, but also that less relevant features for local key detection, like for example, the inversion of textural features, which are quite useless to describe the local key. So this kind of features show less signal than other features. In other words, this suggests that our model, which has been only trained on local key detection, can capture human-relevant harmonic features. It has not been trained. So we have these quantitative results, but we want to see also how they can be interpreted in terms of actual musical content. So let's get back to some actual music and ask ourselves a last question. What are the actual musical elements that may lead the model to think that there is a local key change? So let's get back to the example and at the beginning of this part, which did contain a modulation. We can hear it again. And so if we pass this extract to the model, we've got these distances between the LRP maps. And so on our visualization, we see that the relevant attention heads change before and after a certain point. So in other words, there is indeed some signal that there is a modulation according to the model. And so we want to build a counterfactual example starting from this example in which there is no longer modulation according to the model. So this will indicate which were the original musical elements which were responsible for this modulation to be detected by the model. And so we try to follow our musical knowledge about modulation to build such a counterfactual example. So first of all, we know that having a key signature change is likely the synonym of having also a modulation. So instead, let's keep the same key signature as before. You can hear it, what it gives us. So we can hear that there is still a modulation. And according to the model, we also see that there is still this blue zone, which means that there is still a modulation according to the model. And indeed, if we look at the music, there is still a modulation, but another type of modulation. So keeping the key signature is not enough. So let's transpose all the second part into the initial. You can hear it. So now there is no longer this blue part, so there is no longer modulation. However, there is its kind of blue cross, which appeared by doing so, and which means that very locally here, there is a sudden change of attention head relevance, which become very dissimilar with before and after this point. So let's try to understand what are the responsible of this blue cross to have appeared. First of all, an important element that would indicate a modulation is the use here of the F sharp, which is the leading tone for the G major tonality. So instead of having this leading tone, just keep an F natural. So if we do that, we have this distances between the LRP maps, and we have still this blue cross, so it's not enough. Instead, we can rewrite all the initial modulation preparation, which is technically just a 251 into the target tonality. So we can hear it. And so now there is no longer this blue cross. And so when this blue cross disappeared, it greatly suggests that the responsible of this blue cross part was indeed the initial modulation preparation. So in other words, the inner mechanisms of the model managed to capture very high-level relevant musical writing techniques, such as a modulation preparation, even though at the beginning it was just trained to label tokens with tonality labels. And so to conclude this part, having this model explainability approach gives us a view of how the model behaves more than just performance on a task. And so by doing so, we see that a model which can learn much more than just a local key labeling, but also very refined musical aspects that ultimately can match also our musical intuition at some point. So now we have representations to represent music. We have models adapted from NLP to process it. And so now let's use them for actual musical tasks, and in particular for music generation. So in terms of tasks, there can be some tasks which can be seen as common between NLP and NRIA. There are some tasks which can be specific to NLP because of specificity of language, like for example semantics, and other tasks very specifically to NRIA because of some particularities of music, like for example the notion of polyphony or the notion of harmony. So in the following, we want to perform a task specific to music, reorchestration, and we'll use here NLP only as a toolbox to tackle this task of reorchestration. So first of all, let's define what is reorchestration. So first of all, reorchestration involves a change of instrumentation. Like for example, in Beethoven 5, it has been initially written for a symphonic orchestra, but one can reorchestrate it, like for example, for solo instruments or for smaller ensembles. So reorchestration is first about instrumentation, changing the instrumentation, and the second point is orchestral texture. So reorchestration is also about changing the orchestral texture, that is say how the different parts are distributed over the instruments and how to characterize all these parts. For example, here we can listen to this extract from the New World Symphony from Bordeaux, at the beginning of the fourth movement. So here we can hear that the melody is played by the brass, and all the other instruments of the orchestra are playing like very static, sparse chords. Later in the piece, we have this extract. So we have still the melody which is played by the brass, but now the orchestra is playing like very diverse accompaniment compared to the first extract. In other words, we have a change of orchestral texture from the first to the second extract. So reorchestration will be also about changing the orchestral texture. However, what we want to keep is the melody. Like for example, I show here examples of pieces from many styles, from film music to French folk songs to Taiwanese pop music, which all share a common chord progression, which is a kind of Pachelbel canon-like chord progression. So basically, given that they share the same chord progressions, we could write the same accompaniment part. But at the end, what makes each tune recognizable will remain its melody. So in a orchestrated piece, we want to keep the melody. So orchestration are 3 points: instrumentation, orchestral texture, and melodic fidelity. So for that, we have proposed a model that we have called Meteor for melody-aware, texture-controllable symbolic music orchestration, which will tackle this task. You take first a reference piece, and you reorchestrate it for various instrumentations. So for example, a piano orchestra, with various levels of texture, like for example, a denser texture versus a lighter texture, while keeping the melody, what is highlighted in red. And so we want to use here our NLP tools, so our tokenization and our models, to tackle this task only as a 2 points. So let's, first of all, let's talk about tokenization, our representation part. So for that, we have used event-based tokenization strategy for the musical content, but we'll also use tokens as our constraints for our instrumentation selection and also our textual features. And so we have chosen some textual features as bar and track level textual features. So we have our tokenization, and we have to choose now our model. And so for the model, we relied on UseMorphos, which is a transformer encoder-decoder, which has been developed originally for piano-style transfer. And so in some way, reorchestration can be seen as a task of translation in language. And so that's why we wanted to use this model to tackle our task of reorchestration, because translation tasks are also performed with such encoder-decoder architecture. And so now we can perform generation with our model, and textual and instrumental controls with the tokens. So at the end, we now want to perform the last point that I presented, that is to say, ensuring the melodic fidelity. And so for that, we propose a method that we have called inference guidance, which will enforce the melody to represent in the generation. And so for that, we'll first detect the melody. We'll then choose a melodic instrument to play the melody, and it will be during inference that will enforce the melody to represent. Like, first of all, we'll let the model generate what it wants, like for example, a bar token. We'll enforce the instrumentation, and then we continue to let the model generate, like for example, a position and a track. However, here the track is the melodic instrument. So we'll enforce the melodic tokens to be present here just after the track, the melodic track. And at the end, we just want to let the model generate what it wants until the next melodic tokens be enforced again in the generation. So we have our model which can perform reorchestration, so that is say instrumentation, textual control, and melodic fidelity. However, we can think further beyond this task and consider another task, which is lead sheet orchestration, which may be similar to reorchestration. Because a lead sheet is just a melody with chords annotation. But if we translate this chord annotation into actual notes, we can just consider a lead sheet as a simple 2-track sample so that we can perform classical reorchestration tasks on it. For example, we can give this sample with actual notes representing the chord label and orchestrate it, for example, for a trio ensemble. So here you will first hear the lead sheet itself, then crossfade it with its orchestrated version. And so now we have our model which can perform reorchestration and has zero-shot learned lead sheet orchestration. And so now we want to evaluate it. And so for that, we can consider some baseline models, and we can perform first an objective evaluation, then followed by the subjective evaluation that I will only describe here. So for that, we asked some participants to rate the generation based on some criteria. And here are the results of our subjective evaluation. So we see that our model can outperform the baselines on all the criteria. And first of all, we can listen to what it generates with first a reference piece. And this is what Meteor reorchestrates from that. So if we focus on some criteria, let's say the content currency, we see that the worst performing model is Figaro in blue. So let's listen to what Figaro generates. So we hear that Figaro does not keep the melody. And according to the users, it's also the worst in terms of content currency. So it suggests that the melody is very important to say that the reorchestrated piece keeps the same content with the references. However, if you listen well, it manages to keep the pam-pam, which is a very very textual characteristic of this piece. In contrast, let's listen to what Accomontage generates. So we hear here that the texture is lost, everything is blurred out, because it relies on a lychee transcription step. So it suggests also that in order to keep the same texture, you can't rely on such lychee transcription test that would blur everything out, but you have to pass to the model the original texture from the original piece. So we have heard that our model can generate like nice music. So let's hear again what our model can generate. Sounds nice, but if we look closely at the score, if you are a cellist, you will see that there are very awkward fingerings or even impossible patterns. And also, if we put the generated MIDI into a score editor, this is what I've done here, it can produce like errors in terms of enharmonics or even voice separation issues. So this is a question not only for Meteor, but for other models, how to ensure that our generated music is humanly understandable and playable. So this issue of music generation for human use can be a future direction for future symbolic music generation. So let's conclude this presentation with first a recap of our contributions and how we organize this topic of modeling symbolic music with NLP approach. So we structured this around 3 axes, so representations, models, and tasks, for which we have some technical contributions. And so some of these contributions has led to some publications, and in particular, 2 of them stem from international collaboration through my 2 international mobilities. So one 10-day visit in Singapore at SUTD and a 3-month visit in Taiwan at National Taiwan University. So from these contributions and the study of this topic, there can be some limitations, but also some future directions toward adapting NLP tools for MIR. First of all, there can be some limitations and some questions, like first of all, with the choice of the alphabet. Because most of the NLP tools are based on a Latin alphabet, like languages which rely on the Latin alphabet. But we have seen that symbolic music alphabets can be very different from the Latin alphabet. So to what extent can these NLP models be directly applied to symbolic music alphabet? The second question would be on the data itself. Like symbolic music is often considered as a synonym of MIDI, like for MIDI analysis or MIDI generation, but MIDI can be inherently noisy data. So is it really the way to rely on MIDI to perform, like for example, humanly playable generation, or would it be better to rely on other types of data, like for example, music XML or Kern, and in such a way, how can we tokenize this type of data? Another question, still on the data, but more on the quantitative side, is that transformers are built for very large data sets. And in NLP today, there is a kind of run for the largest model possible to be the most efficient possible. But in MIR, since symbolic music data is released at a much more slower rate than text, can this trend of having the largest model for the largest data set possible really follow? And are larger models really the solution for musical programs? So there are issues, but we can still take inspiration of what is done in NLP and adapt it for our musical programs. And what is nice is that the MI community has shown some signs of such practices. Like in terms of model explainability, it's important to understand how a model behaves, but even crucial in creative contexts. So in NLP, there is this kind of, there are multiple ways to do that, like through mechanistic interpretability. And the MR domain has started to focus on that for example, by proposing some tutorials about explainability. Another thing from the NLP domain would be about benchmark. The problem with music is that models are often implemented for very specific tasks, like, for example, my orchestration task. And there is, most of the time, a subjective study to evaluate this model. So how can MIR benchmarks be built? So there is typically the competition, the MIRAPS competition that started last year, and some benchmarks which are also proposed. And finally, more technically, today the use of NLP tools in the MIR domain have become massive with transformer models, but today it has even become standard. Like here, we see that the number of words transformers in ISMIR abstract has dropped here, as if it has become standard to have a transformer in an ISMIR paper. However, there are other models which are becoming widespread, like diffusion models from image processing. But this raises a question, like what about a model tailored for music beyond just simple adaptations of other models, and does this model really exist or not? So to conclude, I have two takeaway messages that I'd like to pass through this thesis. First, in terms of how an MIR project can be shaped, we should think about the three aspects of task, representation, and model, and in particular, identify what is the main contribution of our project. Also, how our task is precisely defined in terms of music sense, and why we have chosen such representation and model. And finally, the other main message I'd like to pass is that we should consider NLP more as a toolbox for MIR more than a motivation by itself. Like, it is not because there are high-level parallels between these two fields that NLP models are efficient, but it's because we have adapted them to our musical products. In other words, we should ask ourselves first musical questions and only see then NLP or other domains only as toolboxes to take inspiration from. That's the end of my presentation. Thanks for listening.
Thank you. So we will start the second set of questions. I will start. Do you? Yes, you. Anna, are you here? And can you start the session of questions, please?
Yes, thank you. Well, congratulations on the phenomenal talk. Is there an echo going on?
Yeah, it's working very well. We are hearing you.
Okay, cool. Yes. Yeah. I read the thesis a couple weeks ago, and yeah, it's really awesome seeing your presentation, and yeah, I feel like in a lot of the deep learning work for music and in general, there's a challenge of it being a black box, and I feel like you're really bringing some understanding back. And I really also appreciate your treatment on the symbolic representations and models and tasks. There's so much care that you put into it that I feel like it gives me a lot of hope on how we can make progress. Maybe I have a question about on the explainability part. So the earlier part of the talk. I'm curious some of the findings you're seeing in analysis, how it might apply to generation, and if some of the understanding might lead to how we can think about controllability.
Yeah. So indeed here I only focused on music analysis, but indeed there can be some. It can be also applied on generation, and in particular, what is interesting, what I have thought initially, is that in generation you can generate something in the same local key. So we know that somewhere in the model there must be somewhere in which the local key is encoded. So what would be interesting in generation is that would be to spot where this information about local key is located, so that we can also use that as our constraint, more or less constraint in terms of local key. So here it's just local key, which is a very specific feature in music, but this can be applied to other things, like for example texture or other high level structures, for example.
Got it. Yeah. And maybe a follow-up question. In language, oftentimes I feel like there's a little bit more specificity in terms of how attribution can happen, and it's maybe in some ways also easier to analyze. For example, there's like very, very early work that shows if we wanted to change the sentiment of a sentence, there's literally like neurons that you can, yeah, you can identify and tweak and be able to change the sentiment. For music, there's I think people have tried to do that for thinking about kind of the emotional expression. And then, of course, that's like embedded in so many layers of how music is constructed. So I'm curious, maybe one question is, do you think when it comes to controllability, I guess the first question, do you feel like the attribution is more diffused and it is harder to, yeah, harder to kind of be able to encapsulate in a very kind of pointed way? And then what are the implications for controllability if that makes things much harder?
Yeah, I see what you mean. I think in comparison with language, either the information is more diffuse or is it more high level. I would say I would first begin with more diffuse because the model we use for our musical task is very large, but we generate just one token, which does not mean anything by itself. Like for example, you generate just a bar token, and etc. So how all these neurons just generate one token, which does not mean anything, is a question of how would say that our information is very spread into all the model. And the second point is the high level in terms of if our model is too high level. We have tested our model on a just mass language model, and we see that tonality cannot be learned through our pipeline compared to grammar in language, in which for which there is some signal in terms of grammar if we do some explainative result. So is local key too high level to be captured by just a classic model or not, or is it a too difficult task for a model to learn this topic or not? It's a question.
Mm-hmm.
And then in terms of how all these explainability tools can be applied to controllability, either you manage to spot specifically, as you said, the different neurons which are responsible for some features, or most of the time people are using like token constraints, such as what I've presented in my talk. So it wouldn't be about more explainability tool, but more on the representation side.
Yeah, maybe a question about representation. Yeah, it's really amazing how much, yeah, how you've explored that space and also the connection between how you might, depending on the task and the goals you have, how you might optimize for a particular representation. Yeah, I think in general for folks who are outside of the music field, in other modalities, there's a lot of kind of a lot of kind of trend of like trying to use like kind of trying to find like say like a standard representation, but it feels like for music, especially symbolic music, that doesn't seem like I think your thesis is showing that it would really require different representations and different trade-offs. Like there seems to be the sense of like there's going to be a trade-off. So maybe a question is how might that affect how we say like build like pre-trained models, or like like being able to like build on other other people's models that might be, say, like pre-trained and then used for adaptation, and how if the representation for these different kinds of tasks or pre-trained task is different and the representation is different, how we might approach that.
So to me, the representation is very linked to the task. Like, for example, I can't do functional harmony with just event-based tokens, because a node can change function over time. So to me, the direct link between the representation in the task is, can you use this representation for the task or not? And then the problem with also the event-based representation is also that what do you want to do with that? Like, for example, if you want to generate MIDI to perform with it, it's okay to have like time shift in milliseconds or this kind of tokens. But if you want to have very clean sheet music, it's maybe better to have like REMI or other types of tokenization. So for me, it's the representation is very linked to the task, more than the model itself, actually.
Yeah, thank you. I really enjoyed reading your thesis and also your presentation. I know we have a lot of jury members, so I'll pass it on to the next jury member. Congrats.
Thank you, Huang. I will now give the floor to Xavier Hinaut from INRIA, who is the second reviewer of this paper.
Thank you very much for this very nice presentation. So I found the presentation very clear. Very good with the example and similarly the report is very well. Congratulations. And so I have several questions. So first on the tokenization. So probably I will try to select one. Yes, so in the chapter 6, you have some result that DPU with few number of merge can degrade the performance, and also the fact that early merges produce structural super tokens. So I wonder if structural super tokens are useful, and if they are, when will they start?
Yeah. So when are the structural tokens really useful? If I understand well the question. Yes. Yeah. So for me, I would say what is important in music would be more the pitch than the temporal structure. So having the temporal super tokens which are created before is just a base, but is not very useful to have what is interesting in terms of music, but to say pitch. And so if pitch are created way later, it would need so many merges to build these interesting super tokens, so that you have to go very far, by downloading merge to have these interesting super tokens. So to me, having these super tokens, it's too bad that our temporal super tokens are created before our pitch tokens, our pitch super tokens.
So would biasing this creation of super token, like changing the way PPE is doing the creation of token, would be a good idea?
Yeah, we have thought about that. Like, for example, we know that, for example, just would say, like, for example, if we subdivide in terms of temporal structure, if we subdivide our bars into like 32 notes, so there will be 32 notes in our bar. Maybe just if the notes begin at the 0th time or just at the first time on the 32, it would be more or less the same. So why not merge this? Why not create such super tokens, even though it's not identical, but it's the same? So it would be a flex by pair encoding in which we can merge tokens which are similar but not necessarily exact. And so we can bias this algorithm to create our more interesting supertokens before. So it's been an idea, but has been long.
And yeah, and so also related to the increasing size of the vocabulary of tokens, I wonder if it's more difficult in using the natural language processing to settle a limit to the size of the vocabulary. In particular, the fact that there's a finite number of languages, but maybe I don't know how you can linguists to say it's about 6,000 or 7,000. Kind of agree on this, but could we agree on a number of definite number of music?
It's kind of hard because which type of music is, for example, contemporary music more difficult in terms of language than Baroque music, in which everything is well structured, etc. So that the supertokens for contemporary music, like for example the decaphonic music, would be very, very large to have like even pitch supertokens that will include pitch, while our supertokens in Baroque music will already include like even, for example, like at the beginning you have already like 5-to-1 pitch chords, etc. So it really depends on the style of music you want to have. So having a rule of thumb is quite difficult depending on the style of music. But I would say, like with my experiment, having this kind of 3,000 would be enough. And then even if at the end of the 3,000s there are still a lot of non-interesting supertokens, but in my experiments I thought that between 3,000 and 5,000 using this tokenization also, because also the tokenization plays a huge role in how long you have to train your data. Like here, it's the REMI tokenization, but if you use the MIDI-like tokenization, it's not the
same. So then I have one also technical question. So why did you choose to use the TSLE? Because from my understanding, TSLE is, you can say something about points that are close, but you cannot really say something about points that are far away. For example, you might be able to say more about stuff that are so far.
Yeah, we could use PCA or UMAP, but we haven't had a very technical choice on that. So we just use it because it's practical.
Okay, so there's no. And so, in the discussion, we talk about this, in the end of the presentation, we talk about this playability. And I found this interesting because that's something also related to some things I see like sensory motor learning and vocal learning. The models like imitate how songbirds want to sing. And so they have to perceive some sounds and map them to produce motor elements. And there's some theories that say there's an auditory motor representation in the brain. And so it would be interesting to have such auditory motor representation also in transformer and tokenization.
Yeah, I have thought about this. I have a little bit two ways. One more on the, as you said, about the auditory motors. So as token constraints, it would works as token constraints. Let's say that for each instrument we say you can't have this shift in terms of on your fretboard, for example. So in terms of token constraint, but here that will cause the problem of how long the constraint token added before the musical sequence would impact the total sequence length, because there can be a lot of constraints. And the second view I had is that you generate first that, and afterwards you correct what is not playable. But here you will need more human knowledge about what can an instrument play. Like for example, a piano you can play like 10 notes at a time, but for a violin it's not the same. So you have to have this human knowledge of each instrument to control when a track is generated. Is it correct? Is it not correct? So it's a little bit these two ways, either on motor constraints before appended into generation or afterwards correction.
Okay, but since you change the absolute encoding of pitch, for example, to interval-based one.
Yeah.
Putting this interval-based, the thing that for maybe for piano you can do two notes that are too far away.
Yeah.
Very simple way of saying it. This interval-based could maybe be hard to do this.
Maybe, but I guess it's not enough because, for example, for a piano you can play one note and one note here, but on the violin it would be the same interval, but you can't play. So again, it has to be specific to each instrument, and again you have to have knowledge about each instrument by itself. So is it a way to really do that? I don't know if it's not enough just to have hard intervals instead of absolute pitch.
But it's too difficult to make this. Are there some knobs to make this constraint? Like what instruments can play?
It would really require a lot of human knowledge, I would say.
So we don't have much knowledge.
We can do it, but you have to be specific for each instrument. So it could be just long.
And yeah, and so I've also learned that one of your PhD directors is like Songbird, and I actually also like Songbird, but I also studied a bit how canaries, for example, make some sing. And the particular thing about canary song is that they are very complex. They change across time, and it's difficult to. So they have long time dependency of language. Like 4, 5, 6 elements to predict what the next one. And it's difficult to, and we seem to, so there are chunks of elements that always come together, but they can, sometimes they are rolling, so it starts one and maybe you escape from one. And so I would like to have the same kind of vocabulary as there is in music, for example, talk about modulation, I don't know. But so how, so it's a general, how would you speculate? So, like the work you have done, very interesting work on this tokenization, adapting everything to music, could be used, for example, for songbirds where they have the pitch that's changing, the repetition that could change, that it could be a very long syllable. So how could be adapted?
So thinking about that, the first step I was wondering when I was reading your report is, first, can you quantize it? Can you put it not continuous but discrete? First, can a songbird be discrete or not?
Yeah, so we actually transcribe it and put labels, and more 90% of the time it's
okay. Yeah.
Okay.
So, so then it reminds us, with the flexibility I just talked about just before, like having something which is not exactly the same but similar, so that you can find these canary words with this kind of flexibility, I would say.
I'm not sure understood
So either it's a tiki or ti, maybe it's the same words, so that the flexi could create this kind of canary words, so that it can match each canary song to see if the same song or not. It's not really listenable.
Okay. You have time for that question?
Yeah, you can ask.
Yeah, also what you say about polyphony and also that music, there's a lot of things that happen together. In text, it's not really limited by this transformer architecture, it's one token per token. But in speech, we have different things like the prosody, the rhythm, and so what are so I'm not enough familiar with the last one in speech, but is it possible to imagine we have this transformer with various tokens at the same time, or a different way to put this?
For text?
No, for speech. Well, for speech like music or.
I would say for speech, what is first of all, it's what is in speech is not necessarily encoded in text. Like for example, if I say you play an instrument or you play an instrument, it's not the same meaning. Like the first one is you, which is important, and the second was the verb play, which is encoded in the speech, but not if I have written that on the text. So can you use tokens, more tokens to encode what is important in the context of my sentence, what is important in the sentence or not, can be used as a token, as if it has been like extra tokens in it. Like you have the you important token play would mean that the play is important versus important you play. So it can be a way to encode what is not encoded in text, but capture well what is encoded in speech.
And maybe my last question is just so this interval-based tokenization compared to this absolute one, what would it change for the human perception? Because you can recognize the music because you know, for example, the actual pitch, but if you know if it's a relative one, it could be a cover. So is it then becomes more difficult for classification? Or signature of the music, or
yeah. So for someone who has not perfect pitch, so it's the same to have intervals, just to have intervals instead of just perception. But then when put in terms of computer science, we see that having intervals is better for specific tasks. In particular, tasks which really relied on on intervals. Like for example, detecting the bass. Compared to the other nodes, it's an interval which is involved, so it's better. But for example, very large tasks, very high-level tasks like error classification, it doesn't care if it's interval or not.
So if we want to imitate the brain, that you have these different abilities of relative and maybe recognize and the prosody and everything. So for example, in the brain, the language and prosody and music are not processed by the same area. So how would you do an architecture that
either you train your model longer so that you hope that the model learns interval at some point. Either you use a representation which already includes these intervals, such as what I've done here, so that you are sure that the interval is encoded.
Yeah, but I was thinking about the general model because Then you say it's more better for specific tasks.
Yeah. For a more general model, I would say you hope that the model learns the interval at some point. And I think at some point, if we manage to have a good pipeline which spots what you want, you will find intervals somewhere what the model has added.
So thank you very much for
Xavier, before we continue, I just want to mention I forgot one of the jury members, so Marius Bilasco, who is a professor at Université. I had the old version of the manuscript of Chloé. So, but the tradition is not to continue with jury members that are farther away. So I will propose Emmanouil, Benetos. If you're curious, can you ask your question and make your comment, please?
Thank you. Yes, I can hear you fine. Thank you, Viet-Toan, for the presentation and for your thesis. I really enjoyed reading it, particularly chapter 2. We had this parallelisms between music and language. I thoroughly enjoyed that part. And I think it's also really good to have a publication at ACM. Computing Service is really selective as a venue, so well done for this. I'd like to start with a couple of general questions and maybe some specific ones for the core chapters. First question I wanted to ask is, are we relying a bit too much on NLP for solving symbolic MIR tasks? So, you know, NLP, as you say, as you write in your thesis, doesn't really understand polyphony or rhythm, for example. And I'm an audio person, and we rely a lot on computer vision. And is it best to maybe tweak NLP methods to work for symbolic MIR instead of maybe starting from scratch?
Yeah, it's the question I have asked at the end. We are always working on adaptations of other models. So in your case, it's image processing models, and in our discrete case, it would be NLP. But given that we are working with symbolic music, which is discrete as text in NLP, we know it works. So it's nice to begin with that, and we see that we can go very far. But then the question is, we are still using like attention mechanism, which is at the root of transformers. But is there a musical attention mechanism that would, for example, encode directly the notion of pitch, which is not encoded if we use the raw attention mechanism? So I think having the adaptations is a nice starting point. But if we want to have this kind of model tailored for music, you have to think about the inner mechanisms so that it encodes very musical aspects more than just long-range dependencies.
Thanks. And following up a bit, so in your thesis and the presentation towards the end, you mentioned MIDI files and some of the limitations. You suggested some alternatives. Do you have a suggestion on where do you think that the best alternative representation would lie instead of MIDI?
In terms of representation, an alternative for the alphabet typically, something that I have thought is typically Chinese alphabet, at least Chinese character, which is a combination of radicals. In the same way as in music, a note is the combination of a position, a pitch, a velocity, etc. So it would be interesting to see how the Chinese models work with Chinese characters to see if it is adaptable for our musical alphabets. So it has been one of the ideas we've got.
Thanks, that's a very interesting idea. I'd like to follow up on that towards the end. Moving on a bit, all these tokenization methods, they have this sort of artificial ordering. You also acknowledge that. You know, you artificially order maybe the musical features you have there. Maybe you even artificially order the notes if they are simultaneously played in the score. Do you think that is a problem, again, so stemming from the limitations of NLP?
Yeah, for me it's a big problem because typically the attention mechanism doesn't care about the order of the tokens. But here, at least no, the attention mechanism cares about the order of the notes, of the tokens, but in music, given that it's polyphonic or multiple instruments at the same time, or features at the same time, we don't care about the ordering of the feature. So, yeah, indeed, this musical attention could create have to keep to take into account this artificial sequentiality. So if we still rely on NLP tools with an attention mechanism, this attention mechanism has to do it. And indeed, what I've in this project about music generation, here I have arbitrarily put my melodic tokens directly after, but I could put everything else. It's practical because in terms of implementation, it's practical, but it would be interesting to see if I put the melodic tokens elsewhere, is it more interesting or less interesting than if I have put my melodic tokens elsewhere? So yeah, the artificial sequentiality is kind of important for in our adaptations of NLP.
Thanks. Good answer. Right. So moving on a bit on your technical contribution. So in chapter 6, you have your first technical contribution on the intervallic representation. One thing I wanted to ask is, so you apply this for a particular tokenization strategy, REMI encoding. You show that it works. Do you think that this kind of interval tokenization strategy could easily be applied to other encodings beyond REMI?
I think it's applicable at the moment that you have a pitch token somewhere, given that an interval is just defined by a difference between two pitch tokens. So here, indeed, I have only used the REMI tokenization, but it would be interesting to see if other tokenizations would behave the same. So typically, the MIDI-like, what would be interesting is that the MIDI-like is typically a time-relative tokenization. Let's say it's time shift, so it's relative between time, but not in pitch. So what about MIDI-like tokenization with intervals, so that we have both relative pitch and also relative time? So it would be interesting to see combining all these relative aspects in terms of time and pitch. It could be interesting. But here we only relied on the REMI tokenization because we wanted to tackle tasks in which sheet music from sheet music data, so that everything is well encoded. So that's why I have chosen this tokenization.
Thanks. Yeah, and speaking of relative pitches, so I understand that you use like the first pitch to be like your center, and then from there you include like the relatives of pitches across the two dimensions. Have you thought about using maybe like the tonal center, like the tonic of a piece, instead of just using the first pitch that comes?
Yeah, so we have proposed actually not only this first pitch as a reference, but actually it's a choice of a reference encoding, like a first reference that could be the melody from which you put the pitch interval from the melody, the skyline or the baseline. But it can be, yeah, the reference, which can be, for example, the lowest note, there can be the tonal center, there can be the highest note, or there can be either like the first note of the bar. So having this kind of pipeline to build an interval-based tokenization gives us a lot of options to have this interval-based tokenization.
Thanks. Yeah, that's a little flexible. Great. Moving on the next chapter, the next contribution we had, that was the exploration of attention-based inner mechanisms. So one general question I had from your thesis and the presentation, do you consider to be a difference in terminology between explainability and interpretability, or do you consider them to be interchangeable?
So for me, actually, in my context, I have considered that explainability and interpretability was the same. But in the literature, indeed, there have been some differences between interpretability and explainability, in the sense that, for example, interpretability focuses more on the relation between the input and the outputs, while, for example, explainability is more about how the model behaves inside.
Yep. Exactly, because that was my understanding of the literature as well, because that's why I had to ask.
Yeah.
But so thanks for correcting.
Yeah, in my case, I consider as synonyms. So in my, it would be more about explainability what I'm doing, but yeah.
Great, thanks. What I really liked about this chapter was the finding at the very end, where you sort of maybe reveal that all these big pre-trained models don't really learn tonality. And I thought to ask, what would you hope that a pre-trained model like that would learn in a symbolic music sort of scenario?
So this is that. So actually, I didn't hope that the model learned local key, because for me it was already a very high level feature. But I was hoping that maybe it learns very small features, like typically intervals for mass language model, or like even what is the notion of, for example, what is a bit, for example, this very low level feature. However, for other models, like generative models, I hope that there is somewhere this notion of tonality, because when it generates a music, we are still in the same tonality. So it must be hidden somewhere in there. But in my mass language model, given that it has not been trained to generate tonal stuff, I didn't expect that such high-level features could be detected directly there.
Thanks. Yeah, that's perfectly fine. Great. Last technical contribution, Meteor and reorchestration. Thinking about like the coherence of your thesis, as part of Meteor, you did need to do some tokenization. I understand you used a REMI-like tokenizer for this. Did you consider to use your own proposed tokenizer back from previous chapter for Meteor?
Yeah. So actually, I didn't thought about it. However, we managed to tweak a little bit the original tokenization of Muse Morphos, which was a typical REMI plus tokenization, in which there was absolute pitch. Here we use pitch class and octave. So that what we are thinking about is that it will learn that, for example, the contrabass plays octave, low octave, versus the violin, which play high octave. So it was our only tweak of this tokenization. But having the interval-based tokenization was, I didn't consider it, because we are still want to generate things in terms of actual MIDI content, so that we don't have to choose a first note. So we still rely on absolute pitch, but encoded with pitch class and octave.
Great. Just a couple of final questions from me. Summing up on your thesis. So, and one of your answers to my questions was about, as an alternative to MIDI, to use Chinese characters as a way to encode symbolic music. Coming again from the audio domain, I see quite a lot of models which appear to be cultural agnostic, try to embrace diversity in music. Still, quite a lot of the symbolic MIR models are very much sort of culture specific to a particular genre, style, culture. They support staff notation and so on. Do you see any issues with cultural diversity on how sort of current symbolic MIR trends are going?
In terms of cultural diversity, so most of our data sets are all biased toward tonal music. So of course, you wouldn't generate, like, for example, the decaphonic music from a model. But in terms of diversity, you are also very biased towards either pop music or classical music, but not on folk songs, for example, which are more, for example, monophonic or this kind of data sets. So the problem is that if we want to generate like tonal music, it's good enough. But then if we want to generate folk tune music, is it enough just to fine tune a model which has been trained on tonal music on a more smaller community music or not? Given that maybe it's not the same language, it could be a question. However, for our purposes of generating tonal music, I think it's good enough, I would say, the data sets we have.
Thanks. Right. Last question for me. You mentioned about evaluation towards the end. So in NLP, you have these generic objective metrics like the blur and the rouge and the other spice metrics and so on. Whereas in MIR, you say that people do a lot of subjective studies, listening tests, and so on. Do you think that the trend should be for MIR people to try to create more objective metrics like NLP, or should we be convincing the NLP people to use more subjective evaluations for their studies?
I would say for music, the subjective evaluation is still important because it's very, as the word says, it's subjective, like music is subjective. But we also need some common metrics in INRIA. Like, for example, typically, the way I have evaluated my model for reorchestration is that I have to tweak the other models which were not trained on reorchestration so that it can perform the task. So can we rely on common metrics to compare a model which has not been trained on the same task as us, to compare also with our metric, with our model, sorry. And so, but the problem now is, what is a common metric? Is the perplexity enough? Is just, I don't know, the pitch similarity enough or not? It's an open question, but I really think that we still need subjective evaluation for music, typically music generation.
Thanks. That's great. That was all for me. Thank you.
Thank you, Emmanouil. I will let Chloé, Braud, Chargé de Recherche CNRS, comment on last question. Chloé, you hear us?
Yeah, thank you. I want to thank you again for your thesis. I really learned a lot. So I'm not coming from music, not even speech. So I hope my question won't be too many. But yeah, the amount of work you presented is very impressive, and yeah, it's spanning 3 very different domains, 3 complex aspects of the learning problem, so representations, explainability, and generation. And you managed to take from NLP what you need, but you also clearly state and discuss what you needed to adapt. And I think it's very interesting also from the NLP point of view, where in fact we are using these NLP models for anything without really looking at our data, often, even within NLP, and for other tasks. So thank you and congratulations for all your work. I was, of course, very interested in the chapter on and all the remarks around the thesis about the differences between language and music. So my first very naive question is, so it seems to me that speech analysis and audio music are closer than text processing and symbolic music. So why at the beginning did you decide to start with this kind of problem? And do you think there are other problems when you try to adapt speech models to audio music? And maybe do you know if there are better performance when you try to do what you did here, dealing with audio music and speech models, compared to dealing with symbolic music with text models?
Yeah. So for the first question,
clear? No.
Sorry.
No.
For the first question, so it was why did I start with symbolic music? Because in audio music you have only samples, while in symbolic music you have already notes, which is already a very high level feature compared to just audio samples. So that we hope that starting from high level features can get us to even higher level features, so which is typically harmonic analysis that are presented. The second question was about audio. Is it easier to adapt audio models from speech to music than text to symbolic music? I would say for audio and speech, it's still the same type of data in the sense it's still samples, audio samples. While from NLP to symbolic music, you are switching from subwords, words, etc., to tokens like position, pitch, like a very different alphabet. So for me, it would be more difficult to pass from NLP to from text to symbolic music because of this difference of alphabets between the two domains. And there is a third question, but I forgot.
It's just if the performance of, I don't know if there's a model for orchestration, based on audio.
Yeah.
I don't know if it exists. Is it in general better than trying to start with symbolic music?
Yeah, I have never seen a generative model for audio for reorchestration. Because for reorchestration, you have first to do voice separation, so that you have each instrument one at a time, so that at the end you can also generate one instrument at a time. So that's why also to answer to go back to the first question, having already this separation in terms of instruments can allow us to do reorchestration compared to an audio model.
Okay, makes sense. And also, so a different question, but you say that music is not performed and that music has an aesthetic function, and so all contrary to language. So I was wondering if it would make sense to look at work on, I don't know, plays for NLPs, where you also have metadata on a different scene in theater, I mean, and where it's made to be performed too, or poetry, where maybe syntax is more creative, let's say, because these kind of texts are more maybe closer to what you have in music.
Yeah, I would say music is more closer to like typically what you said, poetry, because you have already the structure in poetry. Like in terms of classical classic poetry, this kind of classic structure in poetry would be similar to our structures in music. However, in terms of, I wouldn't say that just because plays are performed in the same way as music is meant to be performed, I wouldn't say that it's a motivation. It's enough motivation to put them on the same scale. I would say it's better to have this parallels in terms of structure in poetry and structure in music than just the goal of plays versus music.
Okay. Yeah, I wanted to go back to this diversity. So I was very surprised, in fact, by the diversity of the datasets used. So mixing in general data from different musical genres. So if I remember well, it's classic music and pop music mostly, but very different, and different eras also. So even in classical music, I assume that there are large differences between different eras. So in NLP in general, we think that if you mix genres, it could be better for your model because it will be more robust, it will help generalization. But at some point, it could also be detrimental if the gap between domains is too large. So in general, it can be seen with the vocabulary or the type of structure involved. So I was wondering if you feel that it's something that could happen in your models or in general in developing models for music.
Yeah, I'm quite sure it would.
Sorry.
I'm quite sure that data set you put into the model impacts the way the model will generate something. Like if I put pop music, it would generate pop music. If I put classical music, it would generate classical music. But however, there is a higher level of this genres, which is tonal music, which groups everything, which groups at least classical music and pop music, so that you can generate tonal music. But you can't expect the model to have learned tonal music and generate only classical music. So it can be detrimental to have too many genres in your dataset if you want to generate only one specific genre of music, I would say.
Good. But you don't see some kind of mix? I don't know, is it possible that your meteor system produces a pop reorchestration of some classical music without really asking it, but just because it sees something pop music in its data?
I don't know if it's enough, because typically, if I have trained on classical music, but when you are thinking about a pop song, you have typically a drum set in your head. But in classical music, you have never seen a drum set somewhere. So would you say that you are generating pop music without a drum set? I would say it's complicated to think pop music without a drum set.
But yeah, what I was wondering, if you have hyperparameters for meteor, so I think it's rhythmicity and texture, if I remember well. So are these parameters very linked to specific musical genres? So if I say that I put a lot of rhythmicity and I don't know about texture, but you can have something that is closer to pop or something that is closer to another genre?
would say the textual.
Maybe not pop. Yeah.
The textual features we have chosen. I
Sorry.
think it's it can be applied in many genres, but not specific to one genre. So that you can have high rhythmicity classical music, high rhythmicity pop music, but it does not define if it's pop music or classical music. Just changing these textual features.
Okay. And yeah, and do you think there are genres, except for atonal music? I understand that it's very different, but are there genres of music that would be more difficult for your model to adapt to? I mean, either for the representation parts, when you try to build a representation for your problem, or when you try to generate new partitions. Do you think it would be? I don't know. I was thinking about maybe hip hop or very specific music, but it seems very specific to me, different from the one you have.
I would say, typically, I would say like maybe jazz would be more difficult to model than tonal music because of the for example the complexity of the chords in jazz, in which there is much more extensions, which gives the color of jazz compared to tonal music, where it's less playing on this kind of extensions of the chord. So just with one comparison about between jazz and classical music, jazz would be more difficult than classical.
So in that case, you would try to adapt your model already fine-tuned on classical music, and did you think about the way to adapt?
It would be a way to
genre of music, or?
Yeah, it would be a way to adapt this by fine-tuning our model. But then the question is it enough? Maybe, given that it's still music at the beginning, but just another type of music. So maybe just pre-training on tonal music and then fine-tuning on jazz music would be a way to have this kind of generative model.
I was thinking, because at the end you also talk about lighter models, and I was thinking about all the PEFT, so parameter efficient tuning methods we have in NLP, and for example for multilingual problems we can use the so-called adapters, where you fine-tune only a small part of the model and then you can do transfer while keeping some information of the general task. So I was thinking, if you think that different genres could be something close to different languages, and then you can also have this kind of mechanism like adapters or other techniques to not try to fine-tune everything and keep all the knowledge you have about tonal music, as we try to keep this all knowledge about language we have when we try to adapt to another.
Yes. Under the assumption that we can have some similarities in terms of genres, which may be true. Like for example, Baroque music and Renaissance music would be much more closer than pop music, for example. And so maybe having this kind indeed of I have pre-trained my model on a specific genre, but then fine-tune on a very near genre would be much more efficient than if you train your model, for example, on hip hop and you want to generate Baroque music. So indeed, there is this kind of similarity between the genre you have to take into account when you want to create this kind of adapter.
The thing is, do you think you have a different vocabulary? When I think about your work on representation, do you think you have a different vocabulary between different genres? So you really need to adapt as for different languages, or is more a question of domains and there are some specificities in the way it's organized overall?
I don't know if playing on the representation play something on the end, because it is, at least if it's still encoded into notes, we can still use the same alphabet and representation, but it will be how this alphabet is, what is the shape of the sequences at the end, that would define what is the genre, more than the alphabet itself.
Maybe the super tokens would be different? Or?
Yeah, it would be more the super tokens, I think. At least
the super tokens?
If we want to put a byte encoding somewhere, it would be more the super tokens that are different, more than the original alphabet.
Okay, but the group-in strategy, if the group-in strategy is a bit different, maybe you need a different model to adapt to a different genre. But and last question on this part is for atonal music then.
Yeah.
I'm very intrigued by this atonal music. I don't know much about that. So what do? You have to start from scratch, or is there anything you can keep?
First of all, you have to find an atonal dataset. I don't know if it exists. If you want to train it.
Let's imagine we are.
Yeah, but I think it would be a very bad idea to pre-train your model on tonal music and then fine-tune on atonal music because it's way too different, I would say.
Okay, so it's not even like different languages or very far away languages, like. Okay, nice. And maybe last question, if I can. Yeah. So I was also very interested in this idea of the grammar of music and the links with language. But I have a few questions because I'm not sure I understood, and I'm not sure I understood especially why there's a focus on syntax on the language side. So, for example, when you describe a framework for grammar of music, I don't remember the name, sorry. You write it's about giving direction to the musical stream to create tension, release, or closure patterns. And what I'm not sure is it at the level of the musical phrase or the entire music piece?
There can be multiple levels of tension and release, but when I think I was talking about harmony when I was talking about that, is more at the level of the phrase that which creates tension, etc. But indeed, there can be some other types of tension or relaxation. Typically, sonata form is based on a subject, a development, and then the development, and then again the same part at the beginning, so that the listener expects this first part to come back in the form. So it's a higher level expectation release kind of structure. But for harmony, it's more at the phrase level.
It's really what I would expect, and in fact, it makes me think about more discourse level phenomena, that syntactic structure.
Yeah.
And in fact, when I read your thesis at some point, I was finding discourse phenomena everywhere. So maybe it's because of me, but the same goes when you talk about polysemy for language, and you say that in music, it concerns both isolated musical note and motifs. So it would be single tokens and sentence if we keep the parallel with language. And so the effect of this polysemy would be local, so constraints on the next notes, or more global with some influence on the next music phrase, or maybe even a segment far away in the music piece. So you have this also global effect.
I think it would be both. In the same way as polysemy in text, you have a word which can mean different things, but you have also a sentence which can mean different things in different contexts. In the same way, in music, if we look at the low level, the notes is not the same function, different depending on the very local context, but a phrase can also be not the same part. For example, in a fugue, it can be the subject or the counter subject. It's more or less the same, but not the same transpose. It's the same phrase, but not in the same context. So it's both. It's at both levels, a low level and a high level.
Okay, so that's why I was a bit surprised about this focus on syntax, because to me there are a lot of things you are describing that are more at the discourse level. So it's pragmatics. It's how in NLP, it's how sentences, or more precisely clauses, are organized together to form something coherent. And when I read some part of your thesis, it was really about how music is coherent. That's what I thought it was about. So I wasn't sure why you didn't look. Maybe you didn't look at what is done for this level of organization in NLP to try to deal with your problem. Or maybe discourse. Discourse is not a modern terminology. Modern terminology is long context modeling.
Yeah. Perhaps because following all the thesis, I was mainly focusing on low-level stuff, so typically harmonic, and not on the whole structure of the music. Like so, typically in the text tense, it will be discourse. Here, I didn't focus on the form of the piece. While there are other works which focus on the form, like creating a pop song with a chorus, verse, etc. But I didn't focus on that on the rest of the thesis. So I would say I have been biased on by what I wanted to do afterwards to describe what I wanted to do in this chapter on music and language.
And yeah, the musical phrases are really because you make a parallelism between this and sentence. So it's really this atomic unit that you can break into subunits that would be meaningful, that would have a function with other segments. I'm not sure about the definition of musical phrase because it doesn't seem to be very clear in music literature. You say cadence, you say I don't know another definition, but I wasn't sure about that.
Yeah, the musical phrase is very not well defined in the musical literature, but we know at least that the musical phrase it is at a lower level than a full song, or at least a chorus, a part of a form. So I was more focusing on this lower level part than the higher level.
Because a very interesting thing is when you talk about these super tokens, you take as an example a discourse connective, in fact. So it's on the one hand, and it's for me it's really like we are talking about these pragmatic links of narration, for example, and I was starting to see discourse variation everywhere, and I was thinking that maybe a variation in the melody is some kind of restatement that we have in discourse. And in fact, discourse is considered more universal than syntax because all languages have this kind of relation where you have support or and at some point you also mentioned argumentative versus narrative texts, and I was thinking, do you think we can say that music is also organized such as this kind of things we have in language? So we have narrative music, we have relations in parts of the music that would support or contrast with other parts, and something of this kind.
Yeah, there is this kind of segmentation thing between language and music, so indeed there is this kind of so more on the discourse it would be higher than the document, or at least at the level of the document. In the same way as in music, it would be as the structure of the score, which would describe the discourse in text. But given that I'm talking about more my super tokens, which would be more at the word level, etc. So it's a very lower level than our musical structure.
Okay. You didn't find other super tokens that are meaningful to express this kind of relations between different parts of the music piece?
No, because it was not long enough to have typically a musical phrase. It was just small motifs in our super token.
Your super tokens were small motifs?
Was not long enough to go beyond the musical phrase.
Okay. I think you should state also in your thesis that NLP researchers should take a look at what is done in music too, because it's very inspiring to see what happens in other modalities also from our point of view. I think I'm done.
Okay, thank you, Chloé.
Thank you.
We'll let Marius Bilasco, so the examiner, ask questions.
for the presentation and for the report. I'm not a specialist of NLP, I'm not a specialist of music either. I'm doing computer vision in my research. Yeah, it was nice to discover the way you can try to build parallel between these two words. But there was one thing that I was lacking is what can we see as a solved task in MIR, and what is the task that should be still, the task where the research should be still very intense. And then at the end you said that basically in this community you are lacking good benchmark. And then I said to myself, yeah, but maybe you don't have good benchmark because maybe you lack a good structure of what's the important axis of research in the community. I mean, I think that they are there and the community is built around them, but I'm missing a bit this picture of what's important in MIR. Then you have selected some, you have seen some subject that you would actually like harmonic, lead, the key detector and so on. But what would be, from your point of view, the fundamental task that one should address when he wants to say, I'm doing new research?
I think it's actually what is actually done in the MR domain. It's a lot of generation, which is a task which is not solved. Because typically what we want to do when we are doing music is to create music. And so I think what would drive an interesting research would be about music generation, but a music generation approach which is guided through our musical intuition and not just putting a big model and a lot of data. I would say what is not solved and what is interesting today is music generation guided through musical aspects. So that we have this
so related with this generation, with the generation contribution that you had, when reading the manuscript, it was unclear for me what did you bring with regard to the baseline architecture that you have chosen. You have chosen a transformer, then your contribution lies only in the inference guidance, or there are other contributions that you have brought in this?
Yeah, so the main contribution is first to define what is the reorchestration task. That you say are my 3 points into instrumentation, orchestral texture. So it's one of the contributions to define exactly, to propose a new task in the MI domain of orchestration at these 3 points. And then the other contribution indeed is the inference guidance, so that there is a melodic fidelity. And then in terms of texture, it has been done through latent space in the original model, but we also propose to constrain through tokens. So our contribution is mainly the definition of the task and the actual implementations to perform this task.
Okay. This adaptation that you have brought, they are very specific to this specific architecture, or they can be applied to some other context, like you compare with the 2 other works. These 2 other works do not have this adaptation that you have brought to the baseline transformer that you have adapted. So what I'm trying to say, is it the original model that performs better than Figaro or Alpha-Montage, or is the updates that you brought to the model that allows to actually be given?
So for the first question, yes, you can apply our 2 contributions to Figaro and Alpha-Montage. At least Figaro, because Alpha-Montage is quite different, because it adds the melody on top and does not generate the melody during inference. but it's indeed we didn't answer if it was because we have applied to our baseline model mixed morphose, or it is because if it's our adaptations which perform well, or just it was the choice of our computation. So we didn't answer to this question.
And for Sparta's question, so this is related to the fact that you're not certain that the music that you generate is playable by a human. But basically all the scores that you are processing are played by humans. So at some point, don't you think it to be able to get information about what is a playable score by looking at the playable score that your model has been trained on?
So yes, indeed our model has been trained on playable music, but it doesn't generate playable music. So it means that it didn't manage to capture what is playability in terms of playability for you. So is it just a matter of training the model longer so that we have also playability, or does the model can't capture playability? Here we don't have the answer. I don't remember what were the original questions.
The idea is the fact that you have mentioned is the notion of playability, and that the fact that the model is not able to capture it, that's an issue, but maybe the model was not also trained to be able to detect.
Yeah, so that's why, for going back to the question of Xavier, do we need to also train our model with our constraint token on playability so that we are sure that our model will learn also playability? Maybe it's a way to tackle this task of playability by training also with its information of playability.
Okay. And then I have one or two questions on contribution on the interpretability or the explainability. So you presented this nice chart, and I imagine that you have generated them with a specific architecture, like a specific number of layers, a specific number of heads. If you change this hyperparameter of the model, will the observation still stand, or?
We didn't try it, but indeed it's sure it will change because we no longer have 12 attention heads, typically 12 attention heads and 12 layers. But in which sense it will change, we don't know, because in NLP typically changing the architecture, there is a paper typically which changed the architecture of the model, and it sees that there are attention heads which have specialized on two tasks at the same time. In NLP there is this kind of paper. And here, if we have another architecture with less layers or less attention heads, can we see that other phenomena that maybe the model will there are other signals about other features which are trained by which are learned by attention heads, etc. It's a question, but indeed here we have used the original BERT model to tackle this task, and we didn't go further beyond the architecture.
And why didn't you use the model that you have designed in chapter 6? Try to do interpretability of the model that you have done in chapter 6?
Because I was interested in functional harmony, just for my musical preference, that I wanted to focus on functional harmony. And functional harmony is typically trained on this task, on this kind of model with multiple outputs, etc. So we wanted to switch our model to this architecture so that it fits our task more than just taking our model from previous works and tweak them to force them into a task.
And are there any related work that try to study this interpretability issue in NIR?
Yeah, there are more. visualization. But today, most of the interpretability is just using, you have a big LLM which can make chain of thoughts, and you ask it to generate ABC notation, and you want just to look at the chain of thoughts, for example. So it's a way to do interpretability, but more on the generated outputs than on the inner mechanisms. And that's why we want to focus.
Now to the supervisor, so I will start with Michaela.
I'm not going to ask any questions. I just want to and also put some more context that he was on the curriculum for me and I, and we were putting him in opposite directions. We were for us, and he managed to keep cool and offer solutions that would be in between the work and or come up with his own solution. Congratulations for that. Be able to manage and yeah, I hope we still have some work ongoing.
Yes, yeah, you can.
Yes, as Michaela said, I would like to congratulate you, Viet-Toan, for impressive work and successful work. And I was actually impressed by your productivity and organization because they have technology. And in spite of the scientific I think it was a hard because both machine learning skills that you are mastering and also a global view on some abstract interdisciplinary questions that you have also showed a good application, for example, with the reduction of this survey, which demonstrates a strong maturity. Usually, survey written after a lot of reflection, and it's great outcome. And that was great and successful. I was also impressed by your ability to build from scratch collaboration with Taiwan University and great collaborations that reached to publication without your supervisors, which is great. And as Michaela said, another difficulty was managers, and as we are sometimes a little bit excited by the topic and finding very abstract high consideration. For those who don't know, Viet-Toan is of course a musician, but also a composer and choir master, we say. So I just have a very light question you're expecting, which is after these 3 years of questioning on music and language, did this question change something on your own relationship with practice?
I've already prepared this question, so it's nice. Yes, I have. Like just by playing instrument, I know that sometimes I think, oh, maybe sometimes, etc. Like for example, I was accompanying my current choir conductor on the organ, and I messed up my introduction, but she managed to hear that I messed up my introduction so that she didn't start to sing. So did we manage to really communicate as a language between just by music, etc.? I have the thought by playing, but then I was getting music. So I think it changed a little bit about how I think about music.
congrats. This is my first show. And I have a lot of questions, but I won't ask the questions here. I have a lot of questions because I was not very involved in this PhD, and I want to recall that this has started when Louis and Michaela were in the same office some years ago, and this is why maybe the collaboration has started, and this idea emerged, and later, okay, we are searching for someone able to answer that questions, and you came, and you did the job, and so congrats for that. It was not so easy, and okay, so you answered a lot of questions today, and I like again this presentation you gave today, and the manuscript also. It is very rich. Learn a lot of things. And okay, so congrats. And I have noted that you used this expression by Frédéric and Revoir. And I like that because maybe we can say that Frédéric and Revoir, because we will work soon with the team that is not so far from Magnet, and hope that we will continue to work together.
So you're nearly done. As the president said first, I wanted to thank you to be part of this jury, also your supervisor. I have to say that I really enjoyed both reading your manuscript, but also listening to your presentation today. And I will ask not a lot of questions, so not a couple of. Of course, I'm going to be very naive. I'm more from signal processing and a bit of audio, so I will. The first one is about your perspective, the future. So you have plenty of different directions. If now I give you one extra year, what kind of problem you want to tackle and how?
What I really wanted to focus on is my model externality part, but on generative model. Because I'm quite sure that tonal key is hidden somewhere, because it managed to generate like music into a single tonal key. But where is it really located would be really interesting in what I want to see. Because first I would like functional harmony, and model externality gives us a view of how it works internally, and I do like understanding how someone with whom I'm playing understands it. So it would be on externality for generative.
I also enjoy the fact that you say, okay, I want to tackle this problem through natural language processing, but there are also other options. And I have a general question with respect to that. I'm from signal processing, so me, I see music more as waves, say. Can you give us your feedback, your feeling about why it's probably better to use tools from natural language processing instead of signal processing or audio processing?
Because in natural language processing, at least in text, everything is already discrete. In the same way as symbolic music, everything is already discrete. So it's a more direct way to transpose NLP to symbolic music than a model trained on continuous data to our discrete data.
So this leads to my last question. My wife loves music, classical music and things like that, and so I listen to, and she's able to tell me, I like this interpretation, I like all these subtleties. So you see, I'm thinking of interpretation mostly, but even if you consider variation of a theme, I don't know exactly how you call it, but since you see what I mean, like the Goldberg variation and things like that. So let's focus on interpretation. Don't you feel that this MIDI representation is too narrow to go as deep in this kind of very subtle way to represent music? And if so, again, maybe waves or signal give since it gives way more information in the end, like the MIDI file is just a compression of your audio file somehow. Okay, can you elaborate a bit on that?
Yeah, sure. MIDI data is clearly not enough to say that it's music. Like I wouldn't hear this kind of MIDI stuff just for fun. So having this interpretation gives us more than MIDI, but at the beginning it's still, at least at the beginning, it's still sheet music. So it's maybe better to first study the root of the stuff and then extrapolate to this interpretation stuff, which is much more at a higher level than just the sheet music. And indeed, when we are doing interpretation, maybe it's better to have this signal processing approach than when we are doing sheet and when we are missing sheet.
Do you have any idea how, I know that it's probably a difficult question, how you would code this interpretation, this way to interpret a score in this way or other?
For me, it would be directly in the representation itself. Typically, in the representation, you have the velocity token, which says how hard you press on the key, and indeed on the piano, it's this way. But also in the timing, like sometimes you have some rubato that says some slowing down and stuff like that, and it would be in the time dimension. Typically, what is proposed in the Recherche is that you have the strict timing of the score, and then another token that would say, oh, you have waited a little bit longer so that you have this rubato. So for me, it's directly the representation that you encode the performance information.
Okay, thank you very much. It's time for us to deliberate, I guess. We go to another room. Or we stay here, and so I will ask the audience to come back after, of course.
Okay. Yes. Non, juste ça.
Okay, so I will read the statement that which the jury decide to vote on. Mr. Viet-Toan gave an extremely clear presentation of his work, demonstrating through the quality of his slide and explanation his ability to present complex technical concepts related to both music information retrieval and natural language processing. We also note the fact that these slides were suitable for both an informed audience and novice, and that they skillfully combine high-level concepts in machine learning and music representation with audio and visual examples that allowed the audience to step back and grasp the essence of his work. Mr. Viet-Toan research stands out from other work in the field due to the combination of quantitative and subjective evaluation to validate his methodology, but also other things, together with his international collaboration and reorchestration. The jury also appreciated the availability of online tools and materials which promote reproducibility, and the explainability study that allowed a deep analysis of the models that were trained. Mr. Viet-Toan answer to the many potentially open questions of the jury, which covered a wide range of aspects of his work, demonstrated both his strong technical mastery of the subject and his broad scientific knowledge. For all these reasons, the jury is convinced that Dinh-Viet-Toan has the quality of an excellent researcher or assistant professor, and that he has also the potential to become a high-level scientific figure in his field. The unanimous jury awards Mr. Dinh-Viet-Toan of the degree of Doctor of University of Lille in Computer Science. Congratulations. And there is, oh yes, it's not totally done. So you have also this, if you agree, I think, but probably you will, to read the statement either in English or in French as you wish.
En présence de mes pairs, parvenus à l'issue de mon doctorat en informatique musicale et apprentissage automatique, et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la flexibilité éthique et dans le respect des principes de l'intégrité scientifique. Je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le domaine ou secteur d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. So I have to say some words.
Okay.
I have 7 points, so that is just structured. So first of all, I'd like to thank the members of the jury, Anna and Xavier, for their time to read and to review my very long manuscript. Also, Emmanouil, Chloé, Patrick, Marius, okay? Yeah, for your time today for my defense. And since also you have seen that I do like something which is well-structured, thank you also for being such a well-structured jury with the reviewers with surnames starting with H and my examiner surname starting with P. Thank you very much. For the second point, thank you, Louis and Michaela. You have already read my 8,000-word report on how I have experienced this thesis, and you know that you belong to the part épique de la thèse. So thank you very much for this thesis, and maybe for 2 things that will englobe everything. Thank you for the discussion planante we've got, but also for unsuccessfully trying to make me take holidays during my thesis. First of all, thank you for the discussion planante, for all the scientific discussions we've got, and for being much more optimistic than me on my research topic, and also for unsuccessfully trying to make me take holidays, by also making me discover how I like to work. Sorry for being the one who sets the deadline for you. And thank you also for making me discover what I like in INRIA, what I do not like, etc. In a sense, thank you for making model explainability for myself. Then thank you for the magnet team. Marc, first of all, for being my thesis director, and also for all the people I have met in the magnet team. Thank you notably for forcing me to take a break for the Jeudi Gâteau. And then for the algorithms team, Mathieu is not there, but thank you, Mathieu, for also making me discover INRIA like 4 years ago with the orchestral texture project. And also Patrice and Ray for all the technical things today, and all the people I've met in the algorithms, and all the activities, etc. Thank you. Then I would switch for the people I have met in my mobilities. So first of all, I don't know where I should look at. First of all, people I have met in Singapore, Dorian Elements. Thank you for this survey and these 2 short visits in Singapore. And a huge thank for Eric in Taiwan, which I have learned a lot during my 3 months mobility. And also people maybe who are watching from Boston or Montreal who are that I met during conference during my mobilities. So thank you very much. And then more close to me, thanks to my family. So, je vais switcher en français. Merci beaucoup parce que Quand j'avais 5 ans, du coup, j'ai commencé la musique. Et du coup, après mon deuxième ou troisième cours de piano, j'étais en train de pleurer parce que c'était trop dur. Et maintenant, 20 ans après, je suis en train de faire une thèse en musique. Merci beaucoup pour d'avoir grandi autant musicalement. Et enfin, pour mes amis, tout d'abord mes amis scouts que j'ai pu rencontrer, qui m'ont donné des idées farfelues entre planter cette première graine de la recherche des années bien avant la thèse, à mettre le chant des adieux dans ma soutenance de thèse. Merci beaucoup pour ces idées et pour tout ce que j'ai pu recevoir de vous. Et enfin, les personnes des chorales, que ce soit la chorale interscout de Toulouse, le chœur scout des Flandres, le chœur cathédrale, le chœur Saint-Antoine, et bien sûr les choristes d'Exutémus. Merci de m'avoir permis d'endosser tellement de rôles différents entre choriste, chef de pipi, chef de chœur, violoniste, chantre. Aujourd'hui, je suis un organiste en carton. Et merci beaucoup de m'avoir permis d'endosser tous ces rôles. Et merci aussi pour toutes les amitiés en dehors de la musique. Et enfin, if I have to conclude with one takeaway message, thank you for reminding me that maybe it's nice to see music like LRP maps everywhere and stuff like that, but at the end, maybe music is not only about a sequence of tokens, but maybe much more than that. So thank you very much. And now you are welcome to eat at the pot de thèse with our more or less successful Vietnamese and Asian.
Thank you. Bye bye.
Thank you.
Congratulations.
Thank you, Emmanouil.
Yeah.